So in this lecture we are going to discuss about design of sewers. Sewer is a pipe or conduit carrying sewage. Okay, I told you that sewer is a pipe or conduit carrying sewage. Sewage means liquid wastewater generated from community that is foul in nature, that consists of organic matter. Okay, so let us coming to the our lecture, design of sewers. Okay, generally sewers are mainly designed to enforce two things. One is the to finding the cross section of sewer. So I told you that cross section means it involves diameter of a pipe or conduit, and second one is that finding the slope or gradient. So understanding everyone here. So let's start our lecture. So design of sewers. The hydraulic design of sewers and drains involves finding diameter, slope, crown or invert elevations for each sewer pipe in the system. Generally, so these things three are very important. One is the diameter, slope, crown or invert elevations. Okay. Generally, sewers are designed to run partially full. That means partially full means flow under gravity. Understanding everyone here, sewers are designed to run partially full, the under gravity. This is very important. Sewers are designed to run partially full under gravity. Sewers are designed for maximum discharge. In the previous lecture, we discussed about the maximum discharge, maximum hourly flow. So minimum and maximum hourly flow we discussed in the previous lectures. I told you that generally the maximum hourly flow is equal to 3 times the average daily flow. I told you. So this is very important. Sewers are designed for maximum discharge, that is maximum hourly flow. So for maximum hourly flow is equal to 3 times average daily flow. Again this average daily flow we have to calculate. Okay, so hydraulic design of sewers that involves finding the diameter, slope, crown or invert elevations for each sewer pipe in the system. Sewers are designed to run partially full, that is under gravity. Sewers are designed for maximum discharge, that is nothing but the maximum hourly flow. Another thing is that the slope of sewer pipe is based on the permissible minimum velocity at minimum flow. So the slope of sewer pipe is based on permissible minimum velocity at minimum flow. Understanding here? So slope of sewer pipe is based on the permissible minimum velocity at minimum flow. Sewer must be checked to ensure that at minimum hourly discharge, velocity generated should be greater than self-cleaning velocity. Understanding here, sewer must be checked to ensure that minimum discharge velocity should be greater than the self-cleaning velocity. Okay. In order to avoid clogging or silting of sewers, it is necessary that sewer pipes to be of adequate size and laid at such a gradient to generate self-cleaning velocities at a different possible discharge. Generally, the freeboard also provided in sewers and drains. Freeboard generally the sewer pipes of sizes less than 0.4 meter diameter are designed as running half full at maximum discharge, and the sewer pipes greater than 0.4 meters in diameter are designed as 2 by third full at maximum discharge. This is very important. Provision of freeboard in sewers and drains is for less than 0.4 meter dia, designed as half full. For greater than 0.4 meters dia, it is designed as 2 by third or 3 by fourth full at maximum discharge. So these things are very important in finding of the design of sewers. Okay, so let me revise here. The hydraulic design of sewers involves diameter, finding of diameter, slope or invert elevations. So generally these are designed for run partially full under gravity and designed for maximum discharge. There is nothing but maximum hourly flow is equal to 3 times the average daily flow. And also provision of freeboard in sewers or drains are for less than 0.4 meter diameter designed for half full. For greater than 0.4 meters diameter is 2 by third or 3 by fourth full. So understanding everyone this. Next, coming to the difference between the design of sewers and water mains. Generally, we can define it in two ways. One is the presence of solid matter, another one is the pressure. So this pressure is nothing but the pressure pipes, we can say, or water pipes. So first we discuss about the presence of solid matter. Sewage contains solid particles either of organic plus inorganic in nature. They must settle down on clog. They may also cause wearing of pipe material. Hence, the sewer pipes be of such a size and laid at such a gradient so as to generate non-silting and non-sourcing velocities at different possible discharges. So understanding here, so the sewage consists of solid matter, that is organic plus inorganic in nature. Lighter particles remain in suspension while heavier particles settle at bottom of sewers, resulting in clogging of sewers. At low velocities generally these will happen. Okay, to avoid clogging of sewers, the solid particles which settle at the bottom have to be dragged by the flowing sewage. For this, the sewers are laid at such a gradient that self-cleaning velocity is achieved at all values of discharge. Okay, the smooth interior surface of a sewer pipe gets scoured due to continuous rubbing caused by the suspended solids suspended solids present in sewage. It is therefore necessary to limit the maximum velocity in the sewer pipe. This limiting velocity or non-sourcing soaring velocity will mainly depend upon the sewer pipe material. Whereas if coming to the pressure pipes or water pipes, here water mains are designed to carry under pressure, and the sewers here water pipes carried up and down the hills and valleys. Sewer pipes are non-pressure pipes, therefore they must be laid at a continuous downward gradient up to outfall from where it will be lifted up and treated and disposed of. So sewers are designed as open channel flow where in sewage flows under gravity. Therefore, for gravity flows, sewers are laid at a continuous downward gradient up to the outfall point where it will be lifted up, treated and disposed of. So this is the difference between the presence of solid matter and the pressure. Okay. Next, so before we going to discuss about the hydraulic formulas for design of sewer, here there is a term called self-cleaning velocity. So the term self-cleaning velocity, it is the velocity which causes both this self-cleaning velocity. It is the velocity which causes both floating and heavy solids to get transported easily. It may be noted that larger the size of the sewer, the higher is the velocity of flow. That means there is a large size of the sewer pipe size diameter. There is a more diameter of the pipe means there is a higher velocity of the flow. Self-cleaning velocity which causes both floating and heavy solids to get dispersed. Then generally there is a formula called for the self velocity. Self velocity is having the formula square root of 8 k by f into s minus 1 into g into d. Here, here self-cleaning velocity is equal to square root of 8k by f into s minus 1 into g d. Here the term s denotes the specific gravity of a sediment. Okay, the term f denotes the friction factor. The term d denotes the diameter of grain, and the term k denotes here a sediment characteristic constant. It can be determined by the experiments. So understanding everyone here, the self-cleaning velocity is defined as the velocity which causes both floating and heavy solids to get transported easily. So if you have the large size of the sewer, so sewer means a pipe. Generally, a pipe is having the diameter. So diameter is more means higher is the velocity of flow. To calculate the self-cleaning velocity, there is a one formula is called as square root of 8k by f into s minus 1 into g into d. Here k stands for the sediment characteristic constant. It can be determined by the experiments. Another one is the f. F is a friction factor. and S is the specific gravity of sediment, and G stands for acceleration due to gravity, that is 9.81 meters per square meter. Another one is the D, diameter of grain. Generally, the minimum velocity to be generated in sewer is avoid silting. Generally, the minimum velocity is generated to avoid silting, that is equal to the self-cleaning velocity. Generally, this self-cleaning velocity is usually taken as 0.75 meter per second. This self-cleaning velocity is generally taken as 0.75 meter per second. So to avoid silting, we have to maintain the minimum velocity of flow, that is equal to the self-cleaning velocity, that is usually taken as 0.75 meter per second. So here we can see that the difference between the design of sewers and the water mains. There's a water pipes also. Okay. Hydraulic formulas for a design of sewers. As already mentioned, the sewers and drains are generally designed as open channels, except when it is especially required to design them as flowing under pressure, as in the case of inverted siphons and discharge lines from sewage pumping stations, which always flow under pressure. So various empirical formulas which have been suggested for determining the gradients necessary to obtain design velocities of flow in sewers are discussed here. First one is the Chase's formula. Here the velocity of the flow in a sewer, capital V, is equal to C into square root of R into S here. Here V denotes velocity of flow in sewer in terms of meter per second. Another one is the R is equal to hydraulic mean depth or hydraulic mean radius. Very important. R, hydraulic mean depth or hydraulic mean radius, it is expressed in meters. Capital R, hydraulic mean depth is equal to wetted area by wetted perimeter. So in open channel flow, we'll discuss about the hydraulic radius for various sections like rectangle, circular, triangular. For these sections, the wetted perimeter and wetted area will be known in open channel flow. Okay. S is the slope of the sewer or hydraulic gradient. S is equal to head drop between 2 points by length between the 2 points h by L. Here C is equal to Chase's constant. This Chase's constant depends upon various. The Chase's constant depends upon the various factors like roughness roughness of inner surface of sewer, roughness roughness of inner surface of sewer, size and shape of the channel. The channel may be rectangle channel or triangular or maybe circular, so maybe any channel. So Chase's constant, it depends upon the size and shape of the channel, hydraulic characteristics of the channel. So again, this value of Chase's constant can also be calculated by using, again, there is a two formula. One is the Bayesian's formula, another one is the Ganglet Putter formula. By using again these two formulae, we can calculate the Cheggy's constant, capital C. So Cheggy's formula, capital V is equal to C into square root of Rs. V is the velocity of flow in sewer, R is the hydraulic mean depth, S is the slope of the sewer, C is the Cheggy's constant. Okay. Next. Another one is the Manning's formula. This is most commonly used in sewers and drain design in India and United States of America. Here same velocity of the flow, capital V is equal to 1 by n into r power 2 by 3 s power 1 by 2. Here n is the Manning's rugosity coefficient, which depends on the, here there is the Manning's coefficient, which depends on the nature of inside surface of the pipe, material and its condition. So V is the velocity of the flow, R is the hydraulic mean depth, S is the slope of the channel. So these things already discussed here. So Manning's formula is also very important. V is equal to 1 by n r power 2 by 3 s power 1 by 2. Okay. Coming to the, now we'll discuss about uh, the forms of sewers. Generally, there are two types of sewers. One is the circular sewer, another one is the non-circular sewer. Non-circular sewer is nothing but the egg-shaped sewer. There are two forms of sewers. One is the circular sewers, another one is the non-circular sewers or egg-shaped sewers. Okay. Generally, we circular servers, sewer. I told you that sewer is nothing but a pipe or a conduit which carry sewage. So it may be in a circular sewers is the most commonly used for sewers, suitable for diameters up to 1.5 meter. So up to 1.5 meters, circular sewers are most preferable. When variation in discharge is not large, that means there is no non-uniform flow. That means there is a uniform flow, then circular sewers will be used because the cross section itself, it shows that it is uniform. Okay. Used in separate sewerage system. I told you that there are three types of the system: combined system, separate system, another one is the partially separate system. The second one, separate sewerage system, is used in circular sewer. Another advantage is that it is easy to manufacture. So this is all about the circular sewer. And second one is the non-circular or egg-shaped sewers, used for combined sewerage system, whereas circular sewer is used for separate sewerage system. For separate sewerage system, again there will be two pipes, one for dry weather flow, another one is for the wet weather flow. Here, used for combined sewerage system means only one pipe. Okay, in non-circular, water depth is greater for small flows, thus maintaining high velocities to prevent settling of solids. Another one is the better self-cleaning property at low flows, less stable than circular sewers, difficult in manufacturing and construction, and expensive. So, comparing with the circular and non-circular, circular is the most preferable because it is a uniform, easy to manufacture. Non-circular is a non-uniform and also less stable comparing with the circular. Okay, so these all about the forms of the sewers: circular sewers and non-circular sewers. In circular sewers, separate system; in non-circular sewers, combined system will be used. Next, we'll discuss about the sewer materials. So what are the different materials that is used for manufacturing of a pipe that carries the sewage? The different sewer materials, sizes, types of joints, their advantages are summarized here. First, what are the factors to be considered while selecting sewer material means? It should be, first one is the corrosion resistance. I told you that the pipe that is made up of the steel that should be corrosion resistant, and another one is abrasion resistance, strong and durable, lightweight, imperviousness, economy and cost, hydraulic efficient. So in these major factors, the most important one is the hydraulic efficient. Another one is the corrosion resistance, abrasion resistance. These are the factors we should consider while selecting sewer material. Next, classification of sewers and recommended sewer materials. So generally, for house sewer, vitrified clay is mostly preferred. For lateral or street sewer, also vitrified clay. Submain or branch sewer, RCC is used. Main or trunk sewer, RCC is used. Outfall sewer, it is cast iron. Understanding everyone here. Here, sewers are classified under the recommended sewer materials. One is the house sewer. For house sewer, the vitrified clay is used. For lateral sewer, also the vitrified clay. For branch sewer, reinforced cement concrete is used. For trunk sewer, reinforced cement concrete is used. For outfall sewer, the cast iron is used. Sewer pipes. There are majorly three tests are conducted. One is the water test, another one is the mirror test, and third one is the ball test. So water test is mainly used for detection of leakage. Mirror test is used for straightness of sewer line. Ball test is used to detect any obstructions. Uh, Here, these are all physical tests, very important. Next, coming to the problem, generally in a design aspect of the sewer, when we consider some cases, first case is that when when the sewer run full, we consider D is equal to capital D here. That means the total diameter will be considered for the small d in the place of that. That means here small d represents the depth of the flow. When sewer run full, the depth of the flow should be equal to the diameter of the sewer. So that is the condition here. Okay, that is the first condition. When the sewer runs full, we have to consider the depth of the flow is equal to the diameter of the sewer. Okay, and generally we know that discharge formula, right? For discharge, Q is equal to AB here. Q stands for discharge, A stands for wetted area, right? This wetted area for circular, generally we consider circular sewer only. For circular sewer, the wetted area is pi d square by 4. Next, coming to the perimeter, that is a wetted perimeter, uh, that is represented by P is equal to pi into D. This pi into D. Another one is the hydraulic mean radius, capital R is equal to A by P. So these are the cases we need to understand here while designing the aspect of sewer. The case one, it is when the sewer runs full, we have to consider the depth of the flow is equal to diameter of the sewer. Coming to the second case, when sewer running half full. That means this is run full, but for second case run half full. We have to consider d depth of the flow is equal to half of the diameter of the sewer. This is a very important condition. When sewer run full, the depth of the flow is equal to diameter of the sewer. When sewer run half full, then depth of the flow is equal to half of the diameter. So this condition is very important while doing the problematic. Okay, understanding everyone. Similarly, the wetted area and discharge, everything will be same. One thing is that while calculating the velocity of the flow, we have to use the Manning's formula. Okay, understanding everyone here. When sewers of given diameter and slope, velocity of flow is same. A sewer running full and half full, but discharges are different. These things you have to understand. Okay, when sewers of given diameter, velocity of flow is same as the sewer running full and half full, but discharges are different. Understanding everyone, discharges are different when the diameter and velocity of flow is same. Okay, so let us do one problem so that we can clearly understand. A 20 centimeter diameter sewer is laid at a slope of 0.004 and is designed to carry a discharge at a depth of 10 centimeter with Manning's coefficient small n is equal to 0.014. The design discharge is okay. So in the given that data, we can consider first one is the diameter of the sewer given. The diameter of sewer is the diameter of sewer is given is 20 centimeters and slope is 0.004 and Manning's coefficient is 10 centimeters at a depth of flow is also given 10 centimeters. So first we know that discharge formula is Q is equal to A into V. A stands for vector area, V stands for velocity of the flow. When running half full, here the case is considered as a half full. A is equal to, I told you that when running half full, R is equal to D by when running half full, R is equal to A by P. We know that. So area already we know that. So pi d square by 8 and wetted perimeter will be pi d by 2. So we'll get R is equal to capital D by 4. Okay. So by substituting these values here, Q is equal to pi d square by 8 into 1 by n r power 2 by 3 s whole power 1 by 2. So V is equal to 1 by n r power 2 by 3 s power 1 by 2. By using this Manning's formula, we can substitute here. So by substituting these values here, we are getting the discharge is 9.6 liter per second. Okay. So in this problem, mainly you need to understand is that first thing is that what the condition is considered is running half full. When running half full, I told you that the depth of the flow is equal to D is equal to D by 2, right? For circular pipe area is, we know that pi d square by 4. But the thing is that we have to consider d is equal to d by 2. Then it will become pi d square by 8. Similarly, we know that perimeter is P is equal to pi d. But in this case, running half full, d becomes again capital D by 2. Then it is pi d by 2. Understanding everyone here, very simple logic here. When running half full, we need to consider depth of flow is equal to half of the diameter of the sieve. So by considering these conditions, we can calculate the hydraulic mean radius. There's hydraulic mean depth also. R is equal to A by P. We'll get D by 4. Okay. So thank you everyone.